through that the internet online. Today, it's my great honor to have my three good friends from that EPC. EPC, their name is called, the complete name is Institute for Scientific and Technology Research of San Luis Potosi. That three friends work there, and today they will give us that three seminar about that carbon-based environment materials. First, I would like to introduce that our speaker. I think one by one. That's one introduction, and then the doctor will presents the seminar, and then the next I will introduce the next. First speaker is that Dr. Cesar Nieto Delgado. Dr. Cesar obtained his PhD from that EPC. The STEM institute he's working on. He works as the postdoc in Pennsylvania State University, United States, from that 2011 to 2014. 2015, he joined that EPC. Now he's that member of the National System of Researchers. He's that the level 2. He has published JCR paper, 32 JCR papers, 4 books chapters, and 2 partners. That his H index is 18. So now let's welcome that Cesar to give us that first speaking. That's one process. Okay.
Thank you. Thank you very much, Professor Song. Thank you very much. Can everybody hear me?
Yeah, sure.
Okay. I will start the presentation. Can I share my screen?
Okay. So you can share that. Okay.
Can you tell me when you see my screen?
Yeah. Sure.
Okay. Let me put this in presentation mode. Ready. Okay. Well, thank you very much, Professor Song, for the invitation. To me, it's a real honor to be here, to be invited to this seminar. And I hope all the viewers like the information that I am about to share. And well, here is the title of my presentation. I just select a topic that is related to mineral and mineral materials, which is the journal seminar that we are working right now. And I would like to start by making just naming the research project participants. The results that I am about to share with you were mostly collected when I was working at Penn State University. Here is a picture of the group that I was working as a postdoc in 2013. Actually, this is me with a little bit more kilos. You know, life of postdoc is very, very good. When you become professor, is more tough. Anyway, and at that time, Professor Fred Cannon, who is here, was the PI of the group. And the original idea and the original project belongs to him. And most of the information that I am about to show you is from projects and papers that were published at that time. However, right now I am the PI of this project, in collaboration with a company in Europe. They contact me around 2 years ago, asking me for consulting about this project. And well, at the beginning, I told them that I am not the PI of the project, and I just contact them with Fred Cannon, who was the original PI of the project. And because he's already retired, he allowed me to follow up with the project with this company. But anyway, I just want to mention that and show this picture from 10 years ago. This is me. Actually, this is my wife, and here inside this belly is my second daughter. Anyway, I am not sure what is the formation of the audience, and I prepared this presentation to give a brief introduction of what is the iron production and the steel production, just to be in the same line all together. And then I am going to show you some results that we obtained from lab scale to full scale demonstration of these anthracite briquettes that we produce. Anyway, here in this slide, I am showing you a very general picture of how the iron is made. Usually, it starts with an iron ore, and this iron ore, this mineral, which is very common, commonly is in powder form, is sintered by heating to produce like small pellets. These small pellets are like melted in a blast furnace, and the main fuel of the blast furnace is coke. And I am about to explain later what is coke. There are two options, or there are two main ways to produce iron. This is the one that is more common when you are starting from mineral ore. But if you are starting from like iron scrap, which is very common too, the furnace that you use is a cupola furnace. Essentially, the blast furnace and cupola furnace are very similar. Both are a vertical shaft, like a vertical furnace. In the bottom of the furnace, there is some pipes that inject air or oxygen to make the combustion of the coke or any other fuel. And this heat just heat all the components inside this shaft. And that is the way in which the iron gets melted, and you produce some other things. No, the main difference between the furnace blast and the cupola furnace is that a blast furnace is a semi-batch production line, and cupola furnace is a continuous production line. Also, when you are making iron from blast furnace, most common, if you only are making iron, you are going to get pig iron, which is an iron that has a very high carbon between 3 and 4, a very high silicon between 1 and 2, and also very high sulfur and phosphorus. It's like a raw iron, right? And when you use a cupola furnace using scrap iron as a raw material and also coke as a fuel, you get most of the time some iron casting or some iron alloys like gray iron, ductile iron, and some other iron alloys. And it's mostly used to make iron casting, like this kind of products. But anyway, the most important thing that I want to focus in this slide is that the main fuel that both furnaces use is coke. Actually, cupola furnace use metallurgical coke, which is a high quality coke, and blast furnace can use coke, like low quality coke, or there are some blast furnace that use also natural gas and some oils as a fuel. But anyway, all the research that I did it with cupola furnace. And well, if you produce iron, you can follow some other steps, right? You take the iron from the pig iron from the blast furnace, and then you start to produce steel by using some other components, some other furnace like blast oxygen furnace or electric arc furnace, and then you make some casting products, or you make some finished products like this iron or steel rolls for construction or some other things. But anyway, now here in this slide, I am showing you just the numbers about the quantity of iron that is produced worldwide. And here you can see the steel production in tons per year. Around the world, mostly the biggest producer of iron is China, with around 1 million tons per year of steel, followed by Europe, the rest of Asia. Japan produce a lot of iron too. Mexico also produce some iron together with Canada, and you know, you see it's a very demand product. Now, on average, to produce 1 ton of steel, you need around, it depends on the processing, it depends on the production line, but you need around 0.6 tons of coke. 600 kilograms of coke is needed to produce 1 ton of steel. Now, steel is like a final product, like a refined product. But remember, before making steel, you have to make, like, you can produce iron or iron alloys. In this plot, I am including the production in metric tons, global production of different iron and steel products. And you can see in this yellow line that the world production of steel is very low in comparison with some other alloys, like gray iron, like cast iron, like ductile iron. In total, the production of iron together with the steel is around 110 million of tons per year around the world. Obviously, this changed with the years, and here is the number that in average you need to produce 1 ton of iron. You need around 300 kilos of coke, of fuel, to produce 1 ton of some iron alloys. Now, just making the numbers, and this is a very rough number, it's not very well calculated, it's very rough. It should give you, all of you, an idea of how many tons of coke are needed for iron and steel production around the world. And this is around 40 million of metric tons per year. Now, a little bit more about coke. Here I am showing you like a schematic of the coke furnace. This is like a lateral view. It's like if you put a knife on the side of the furnace and you see like the inside of coke production. In the central part, you have like a chambers. The chambers are filled out with the raw material. The raw material to produce the coke, metallurgical coke, is bituminous carbon. Bituminous carbon is a medium to high rank carbon with about between 80 and 90% of fixed carbon. And it has to be a very specific carbon to produce coke. Not all bituminous carbon can be transformed to coke. There are some reactions that have to happen to pass from bituminous coal to coke. And the people that run this industry are very skilled on making the combination of different sources of bituminous coal to produce high quality coal. Anyway, Here is the combustion chamber. The production of coke essentially is the pyrolysis of bituminous coal, COAL, and during this process, the coal powder gets melted, and also all the CO bits just gets released. And because it's a pyrolysis process, you need to keep air outside of the oven, and also the consumption of energy is very high. This is the main chamber. Here, I will show you in the next slide the burners, but here is here is the charging card. There are holes on the top of the oven where the coal fines are injected into the chambers. And once the coke is made, you have like this machine that push all the coke all the way out of the furnace to the other side, and here you collect the coke. Now, the production of coke is a very high energy consumption. It depends on the company that is making coke, but it has to elevate the temperature of the oven to around 1000 Celsius, and that takes from 24 to 48 hours around to have one batch of coke. And obviously you release a lot of energy, and also you release a lot of air pollutants. Here is just a more detailed view of the coke oven process. Here is the chambers that I was telling you that are filled out with bituminous carbon, and here are the burners. It's like a battery, you know, like one chamber of carbon and one chamber of the heating channels. Most of the coke oven that run in Europe, they run with natural gas. In Mexico, they run with oil or some other liquid fuel. And the heat that is generated here in this heating chamber is transferred to the chamber where the bituminous coal is, and all the reactions happen, and the bituminous coal is transformed to coke. Some other important feature of the coke oven is here are the loading holes where the carbon is loaded. Here are the flames of the heating source, and obviously you have to collect all gases to avoid environmental pollution. Here is a picture just to give you an idea of what is a coke production facility. Here are now the coke oven batteries. Here is one person, which should be maybe 180 meters height, and the height of the batteries is about maybe 10 meters. They are very short, because you remember it's a chamber where you put carbon, and then you have the heating source, and you don't want to have a very wide space between carbon and carbon to take advantage of all the heat from the fuel. And this is essentially the coke that is being pushed out of the battery, and because it's at 1000 Cs, at the contact with the air in the atmosphere, it just get ignited. I visit 2 or 3 coke companies in the US and one in Mexico, and what they do is they just apply water to avoid the consumption of the coke. But anyway, now up to this point, the main idea that I want to show you is that it's very hard to produce coke, and is very energy consumption, and also the release of CO2 to the environment is very high. Now, what is coke in essential? It is like physically it's like a rock. It's a very hard rock. One of the main properties of coke is that it's very, very, very hard. And also it has a lot of porosity, but this porosity like macroporous, like a very, very, very open porous, like 1 to 10 micrometers, right? Also, one important feature of the metallurgical coke is that it has a very, very, very good chemistry for the iron refinery. For instance, sulfur and phosphorus is poison for any iron alloy and also for steel. If you have a little bit of sulfur or phosphorus in the steel, the mechanical properties of the final product will be very, very, very bad. You can break a steel shaft if you have a very, very high content of sulfur. And coke has very low content of sulfur and phosphorus, which means that it will not pollute the iron casting. Also, it has a very high carbon fixed carbon, up to 95%. Right now, we are working with the coke from a company in Europe that has 97% of fixed carbon, which is a very high quality coke. Also, it has very low ash. It has to have very low ash because at the end, if you have very high ash, this ash will go to the slag, and is going to be just a waste of material and also of energy, because the slag takes part of the energy inside the cupola furnace. And also, this is very important, it has to have a very low reactivity to CO2 at very high temperatures. As I showed you at the beginning, the cupola furnace or the blast furnace is just a shaft. At the bottom is a fuel, and at the top is like is all the material that is packed and is heat by the heat made at the bottom of the furnace. And you want that this coke survive all the way from the top of the furnace to the bottom of it. You want that no reaction happens when the coke is loaded at the top of the furnace to the bottom. You only want reactions at the bottom where there is oxygen and you start combustion. Before that, you don't want anything. Also, I already mentioned it has very good mechanical properties. It has very uniform size also to allow that all the iron that is melted in this furnace just pass through the coke bed. And also, the porous structure is very important in coke because this pores creates a very high surface area in the coke, and at the bottom of the furnace, when the air is injected, the combustion happens very, very, very fast. That is very important. Now, some environmental concerns during the coke production. Well, first of all, the bituminous carbon that is used to produce coke is very, very, well, is every day is more scarce and also is expensive, right? And as probably you remember, you require to mix different bituminous carbon to make the right chemistry of the coke production. Also, it requires a lot of energy for the production. Also, it releases a lot of CO2, and it's CO2 that is coming from fuel, from fossil fuel, right? Here is just a very rough number. Around 700 kilograms of CO2 is released per ton of coke produced, which is a very, very, very large amount of CO2. And also, there is a lot of waste of energy. The bituminous carbon that is used as raw material to produce coke is essentially pyrolyzed during the production of coke, and about between 15 and 20% of the energy that bituminous carbon has on it is just wasted. Well, anyway, and there are some other drawbacks. And well, just facing these problems, these environmental problems, and just looking for alternatives, there are some research that have been done looking for alternatives. The first thing that that the people from foundries have tried is to use coal with similar composition to coke, right? Here in this table, in these lines, I am showing you just the different rank of coals that we have, right? We had a very low rank coals, which is the peat and lignite, and the medium and high rank low coals, which is the bituminous carbon and the anthracite. When I say high rank and low rank, I mean is based on the carbon content of the coal. The anthracite should have a carbon percentage around between 90 and 95%. And for instance, peat should have around 50% of carbon. In this sense, the anthracite is the carbon that is very close to the in chemical composition to the coke, because it has a very high carbon, it has low ash, and there are some coal mines that has a very low sulfur. However, when people on the foundries try to use anthracite, like they can mine these big chunks of carbon anthracite and just dump it into the furnace, what they see is that the temperature furnace decreases. And this is because, as you can see in this picture, the anthracite doesn't have any pore structure. It's very, 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 like very shiny and very soft, but there is no pores in the anthracite coal. That means that it's a very slow, that is slow the combustion rate and also decrease the temperature of the furnace. Also, they notice that when they add anthracite into the cupola furnace at the top, there is a lot of carbon in dust bath collector. The dust bath collector is essentially where all the gases are treated after they exit the cupola furnace. And this is mainly because the anthracite sometimes have like a small amount of water. And when they pass from room temperature to, I don't know, maybe 300 Cs, which is the usual temperature at the top of the cupola furnace, they just explode. And instead of having the carbon at the bottom of the furnace where you want to have it, you end up having it at the waste. Anyway, here are some references. I am not going to go on detail on that. But they explain just how far they have tried to use the anthracite in the metal casting, in iron production. The most old papers are from Walker Group, also from Penn State University, from 1960s. And well, they try to make some thermal treatments to anthracite, like pyrolyzed anthracite, to avoid the thermal shock. But at the end of the day, it was just a lot of energy consumption. Around 30 years ago, 30 or 40 years ago, in the 1980s, researchers started to try to make a briquette. They grind this anthracite to have a very small particles, and then they bind them together to create like a briquette. And well, they see that they have a very good mechanical properties. There are many binders in iron industry, like for instance, starch, which is an organic binder, collagen, which is one that we are using right now, or maybe some other polymer. But they start to notice that, okay, they have a briquette, they have this solid briquette, and when they dump this or when they make like a thermal treatment, they notice that the binder just burn and all the anthracite particles just shatter apart. And also up to like maybe 10 years ago, there wasn't a study that showed that these binder anthracite bricks can resist all the very hard conditions inside the cupola furnace. And well, here are some reference about it. But anyway, now when we were facing this problem, we were in collaboration with many foundries in the US that we having a problem because of the environmental legislation in the US. Many of the coke production facilities were closed. And they approached to the Professor Cannon research group, and he and all the team start to develop a briquette that can resist all the way from the top to the bottom the hard conditions inside the cupola furnace. And well, essentially what we did at that time to solve this problem is that instead of using just one binder that usually just burn at very high temperatures inside the furnace, we use multi-binder systems. And this multi-binder system was designed to provide strength to the anthracite briquette in different temperatures of inside the cupola furnace. Now, first we start with carbon anthracite fines. The anthracite fines in the US is a low value carbon. It just get discarded when they just grind carbon. When they are mining anthracite mines, they just discard the very small particles. We took those small particles and used it to produce the anthracite briquette. Now, the binder system, as I told you before, is based on 3 components that provides strength in all the temperature range inside the cupola furnace. Here is just like a schematics of the cupola furnace. The cupola furnace is loaded from top. You have at the top like the loading part of the cupola furnace has this temperature between 400 and 600. Then below you have like the preheating zone, which has a temperature between 600 and 1000. And then you have the reduction zone, which has like temperature between 1100 and 1400. Just to remind you, at the bottom there is a coke bed, yeah, that when air is coming inside of the furnace, the coke is burned, and this is the heat source to melt the iron on top. And here is just many tons of material that is a coke, scrap iron, and also some flux that help to the production of slag, like limestone and some other things. As the the cupola furnace is a continuous production line, you always have the flowing molten iron, and also you always have molten slag all the time, which means that you have to provide all the time raw materials during the when the furnace is operating. But anyway, we decided to use collagen as the first binder to provide the strength to the briquette when before it's loaded into the furnace. The second binder that we used was lignin, and lignin will provide the strength on the preheat zone or mid-temperature zone, and then we add to the formulation silicon metal, silicon with oxidation state of 0. And in the conditions inside the furnace, silicon carbide nanowires are formed. And these silicon carbon nanowires connect all the carbon fraction in the anthracite briquette and allow the carbon briquette to survive all the way down to the furnace. A little bit more detail about the binders. Collagen is the binder that provides the green strength. Here is a picture of the chemical formulation of the collagen. Collagen is a protein that is very common in food industry. Here are the three main amino acids that form this protein. We select collagen because it's a commodity that is very common in food industry. It is made in very high ton per year. The way in which the collagen provides binding strength to the carbon fines is by a hydrolysis reaction. Water molecules, when you dissolve collagen, just interact with this carbon change. And then when you dry the collagen, this amino acid, this carbon change, just make like hydrogen bridges between all the components of the briquettes and just make it hard. Now, about the lignin. Lignin is what I spend most of the time working with when I was at Penn State. And essentially what we demonstrate in this paper that was recently published in 2021 in Fuel Journal, we demonstrate that at mid temperature between 600 and 900 Cs under pyrolysis condition, the lignin become a polyaromatic carbon. And this polyaromatic carbon just bind together all the lignin fractions in these temperatures. And the third binder is the silicon carbides. Actually, here is a picture, is a SEM picture of the anthracite briquette after pyrolysis at 14 Cs under nitrogen conditions, I guess. I don't remember very well, but you can see how all the carbon grains are connected by the silicon carbides nanowires. But anyway, well, first now I am going to show you a little bit about the lab scale validation that we did to prove the concept about what about if we use these three binders to use it to bind the anthracite fines together. What we did, well, we make a mixture of the dry components, which is the anthracite, lignin, and silicon metal, and we bind it together with dissolved collagen that we dissolve in water, and we use this dye to produce like a brick. And this brick, we make it just putting the mixture inside this dye, and then we apply some compaction pressure. And we got this like 1 inch diameter, 2 inches high, small briquette. Here is a picture of the small briquette. And the main characterization that we did to validate this concept is, well, we just take this briquette, and when we just apply pressure, which is the unconfined compressive strength, we just use the universal strength machine. We apply pressure with 2 plates, and we record the maximum strength of the briquette. We did it in raw briquettes that we only make and let it dry at room temperature. And we also make it after pyrolysis at 900 to mimic the conditions in the heat zone of the cupola furnace. And then we make a pyrolysis of the briquette at 400 Cs, just to mimic the conditions in the reduction zone of the cupola furnace. And in that way, we just validate that at very high temperature, the briquette will stand together, and also is going to have very high strength. Here is just a picture of the machine that we use at that time. Here is the plates of the universal tested machine. These plates just get together, and you measure the strength that applied to the briquette. And here is just a picture of the briquette after applying the pressure, how it breaks. Well, first at lab scale, we validate the concept just exploring the formulation first. We saw that when we use a different amount of collagen, the UC strength, which is the strength of the briquette just dry at room temperature, it increases when you increase the amount of collagen. Also, it kind of makes an interaction with the lignin that we are using. Also, we explore the lignin, the effect of lignin, which if we increase the amount of lignin, we increase the strength of the briquette. And also, we increase the amount of silicon metal that we put into the formulation of the briquette, we increase the strength. Just one number, if we just to put in context, if we prepare a briquette with 5% silicon metal, we can have a briquette that can withstand 1500 kPa, which is a very, very, very high pressure, and it's coming from the silicon carbides. Anyway, we also explore some production conditions, like for instance, the particle size. If we use very small particle size, we increase the strength. And if we use also, we apply more pressure when we are making the compaction of the briquette, we obtain a more dense briquette and also a briquette with very high or with higher strength. Now, after that, after the validation of the formulation, the main problem is that the people on the foundry didn't believe that this is going to withstand all the way down from the top to all the way down in a foundry, in a couple of furnaces, because they have tried before anthracite briquettes and also anthracite chunks, and they were very reluctant. They didn't like anthracite in the furnace. But anyway, Professor Cano at that time was very persuasive, and he just got funding from some, I think NSF or some other companies, and they say, okay, let me try these briquettes, and if your production just get wasted, I will pay full. Anyway, they allow us to try these briquettes inside a couple of furnaces. And this is the results that I am about to show you. Here is just some pictures. We scale up the production from this 1 inch by 2 inches to this big full-size anthracite brick. This is about 6 by 2 inches in diameter. And the production is very easy. You just mix the anthracite, lignin, and silicon metal. You add collagen in solution, water solution. You make a compaction. Actually, he's Professor Fred Cannon working. And then we have a drying conveyor, because you need to dry this very fast to increase the mechanical properties. And that way we produce around 8 tons of anthracite bricks of this size. Every single like these briquettes were around 2 kilos. And well, we have enough material to produce, to make 2 full-scale demonstrations in Foundry 1 and Foundry number 2, that I am going to call like that right now. And essentially, we didn't make any major adjustment from the operation. We just use the same operation as the regular conditions where the foundry people were using. We use a partial 1-to-1 replacement of the coke by the anthracite briquettes. 1 ton of coke was replaced by 1 ton of anthracite briquettes. In Foundry 1, we reached up to a 25% replacement by 3 hours. And in Foundry number 2, we did 25 replacement of coke by anthracite briquettes, and that lasts for 45 minutes. And what we measured in that time, we measured a lot of things, but mainly we measured the cupola furnace temperature, which is one of the main concerns when you put anthracite in a cupola furnace. We measure stack gases composition, metal casting quality, and also thermal efficiency. Now, most of this information that I am about to show you are in this paper. Here in this plot, I am showing you the iron temperature versus the time from the startup. In open symbols are just regular day operations when they are using 100% of coke. And you can see in these lines that the replacement of the coke by bricks. And you can see in these operations that we have a very stable temperature around 1490 Cs. Even in this point, we have to cut the carbon source or the fuel because the temperature was going very, very high. And when you are melting iron, you want to have a very constant temperature, because if you go very high, then you have problem in the metal casting. But anyway, these were very, very good results, very stable temperature, and also the temperature was within the historical. It's like they were using 100% a coke. Some of the things that the company, this foundry number one usually do is that they make this bump of coke. They just make one load full of coke because sometimes the temperature goes low. In these 3 columns is the amount of coke, extra coke that they use when they are making coke, and in these columns are the extra coke that they need when they were making petroleum coke, when they were using anthracite briquettes. And you can see they didn't use any extra coke. Also, the iron melted per fuel was very high when we were using anthracite bricks, which means that we can melt more iron with less fuel. And just to make the numbers, for the production of this foundry number one, the potential savings is around 1,000 tons of fuel per year. Here is just some data about the metal quality. The carbon and the silicon in the iron are shaded in this gray rectangle, and you can see that the red squares, which is the data from the anthracite briquettes demonstration, are very similar to the days where they were using 100% coke. Also, some of the strength of the iron that was made those days just were within the specification according to the producers. Now, we also made a mass balance and energy balance of how well the heat of the fuel was transferred to iron. I am not going to on detail on these equations and also this mass balance, but just remember that the melting efficiency is how the heat is transferred to the molten iron, and also the thermal the TCE, or the thermal combustion efficiency, is how complete the oxidation of the carbon is made. And you can see those values in this table. You can see that the thermal efficiency is higher when you were using anthracite bricks, which that means that the energy is transferred more efficiently when you are burning anthracite bricks instead of coke. And also the thermal combustion efficiency was high, was significantly higher. Now, a little bit of the results that we got in the foundry number two. Actually, this is a picture of the bottom of the foundry when they are just getting the molten iron. Similar to the previous results, in this picture, I am showing you the time in the x-axis, and in the y-axis, the iron temperature. And you can see the red squares, which are the ones that we got when we were using the anthracite briquettes. And when we start the replacement of the coke with anthracite briquettes, the temperature just went down. We went from 1580 to 1520, which is a lot in foundry. We were very, very, very sad, and we saw that the temperature were down, and we were like, what happened with this cupola furnace? Why in the other one worked perfect, and in this one, which is a different cupola furnace, didn't work? But anyway, we collect data, and when we analyze the data, we got the answer. This is this is actually the production line plot. Here in the x-axis is time, and in y-axis is percentage, and is the percentage of the metallics of the scrap iron that is loaded in the top of the furnace. And as you can see, this is the target. This is the amount of iron that you want to load in every charge. And you can see that at the beginning, this line is the charging, which is in the black line, is very close to the green line. But when we start to add the anthracite briquettes, there was some mistakes when they were charging metallics, and they were charging more. And this is why the temperature went down. And that makes us very happy, because it wasn't not our problem, it wasn't the briquettes, it was because they were charging more metallics. Here is a picture of the loading chart car. This is a car that goes all the way to the top of the furnace. And this is just some personnel of the company that were charging these briquettes, anthracite briquettes. And you can see here is the charging load. Here is the coke. Here are some iron silicate alloys, and here is the anthracite briquettes. And you can see that they survive this very rough handle during loading. Now, the other question that we have when we were using this, when we were in this demonstration, is what about if they survive all the way down to the furnace? Are they really surviving into the bottom, to the furnace? And to do that, to verify that, the cupola furnace has like a tuyere. The tuyere is like a small window where you can see how the iron is dripping, is melting, and also you can see how the coke is making combustion. And we were just there, just taking pictures to see if we can be able to see some of the anthracite briquettes. And we have lucky. We saw, here is a picture. Actually, I have a video. But here is a picture of this round shape of the anthracite briquettes, and this is all the way down to the furnace. That way we prove that the anthracite briquettes can be used, and also it survived all the way down to the furnace. Anyway, I'm about to finish. Just conclusion about this part. We demonstrate that the anthracite briquettes perform similar to the metallurgical coke, at least to a replacement of 25% of substitution. Also, the bricks proved to be capable to survive the harsh conditions of the cupola furnace, as seen to the tuyere window in both demonstrations. And also higher levels of anthracite bricks substitution will be accomplished. We didn't do that because we ran out of anthracite briquettes. We only made 8 tons. But it was a very successful demonstration. Now, a little bit, I am going to take just 2 minutes just to show you what we are currently doing at EPC. Here is a picture of the group at EPC. This is me in 2021 when I have a very long beard. And here is a lab that I just borrowed from some colleague. And we start making some briquettes in San Luis Potosí at EPC. Actually, Rene is one of the collaborators of the project. Here is Rene, but he has a mask and you don't recognize very well, but here is Professor Rene, who is about to speak right now. Anyway, we are making materials, we are making briquettes to do the validation of the raw materials for a company that is about to produce these briquettes for production, for the substitution of coke. This company in Europe produced coke, but they have seen that in very midterm, the production of coke, at least in Europe, is going to be very, very hard. And we did some validation of the raw materials, collagen, lignin, silicon, and we make these very nice briquettes, ship it to Europe, and they test very well in some furnace. We are making a big problem with these briquettes is the drying conditions, because when you dry very fast these briquettes, you start to see this kind of cracks. And this is very critical when you try to scale up the production of these briquettes. The company have in mind to make like 500,000 tons of briquettes per year. And the drying, if the drying takes 1-2 days, is just going to take a lot of time and money. Also, we are trying to change or make a reformulation of the briquette to make it more cheaper or more convenient. For instance, we explore the quality of different collagen. Also, look for some other polymer that can react similar to lignin. And also, silicon metal is very expensive, and we are trying to find some cheaper silicon source that can be used to make the silicon carbides. Also, the other thing that we are exploring and we are going to start working in this year is, at the end of the day, the carbon source of these briquettes is still coming from fossil fuel. The anthracite is a fossil carbon, and they want to change that. This is bio, collagen is bio, lignin is bio, silicon metal, we can change that to bio, but the anthracite is fossil fuel. We are trying to use biochar to introduce that in the formulation and see what happens. And that's all. Thank you very much for the invitation. I hope that the information that I share is interesting, and here is my email address in case that somebody is interested on contact me.
Okay, okay. Thank you, Cesar.
You're welcome, Professor.
Okay, that is that very interesting work. Yeah, thank you for your that presentation. I was a story to that everyone. I would like that to have that time to have that good discussion with Cesar. But the problem is that we have 3 presentation seminars that morning. So I think that Cesar it's very good that work, and also that I think that our students and professors that should have that very interesting that the work, because that also that we have done some that work related to that your work. So I think that that interesting that students and professors can that contact Cesar through email to have that deeper discussions. So let's have that a warm that also to that Cesar to thank that Cesar give us that so interesting that work. Okay.
Thank you very much, and thank you for the invitation.
Okay, thank you, Cesar. Thank you, Cesar. Okay. Next, that that invite that Professor René Ranquet. Sorry that I forgot to mention that that event that is that the webinar is organized by the journal Minerals and Mineral Materials. So that our colleague Sharon is the organizer. That's good work. Okay. Okay. Next speakers that will be my good friends that Dr. René Ranquet. Dr. René Ranquet got his PhD from that Loughborough University, England, and then that he moved to the United States, the same university, Pennsylvania State University, that to have his that postdoc. That's called the research professors. And then that he back to Mexico, working at the EPC as that professor at the EPC. From that 2011 to 2012, he worked in the Brown University of the United States as the visiting professor. He's that president of Latin America Carbon Federation. Also, he's that president of that Mexican Carbon Association. He has published that 130 JCR papers, 5 books chapter, and 2 patents. He got that over that 5,700 citations, and also that he has graduated that 40 postgraduate students. Rene is that our good friend. He visited our university, Wuhan University of Technology, twice. Yeah, I think that could be that 2018 or 2019. At that time, that he gave us that good seminar. Good seminar. I hope that you can visit us. That give us the seminars that year in Wuhan again. Okay. So that so now I will give that time to you, Rene.
Okay, please. Thank you very much for the introduction. I will share the presentation, and you let me know if you see it. Okay, it's already there, and
yeah, now we can see.
You can see it. Okay. Thanks a lot. Well, I would like to be in Wuhan with you this time, but it's not possible. But I'm hoping that later on in the future, I will be with you once again. I've been there twice, and I like your university very much. And so thank you very much for the invitation, Professor Song. Always, it's a pleasure. So the title of my presentation, I named it like synthetic mineral oxides and hydroxides to grow carbon nanostructures as adsorbents to capture toxic elements and compounds. Considering the carbon-based materials topic that is now taking this very nice new journal, Minerals and Mineral Materials. So I will start, before I start with the examples of the research I want to share with you, I want to show you where is San Luis Potosí, where is CPC. San Luis Potosí is in the central part of Mexico. This is a photograph from the Research Institute. We have about 500 postgraduate students, and about 1,000 people work every day in this institute. So you are always welcome wherever you are around in Mexico. I have programmed my presentation with these topics. First, I will give a very general introduction about carbon materials for the people that is not related with this topic. Then I will give an example about the hydrocarbons decontamination. Then I would like to talk a little bit about arsenic removal. Then I will switch to carbon dioxide capture. Finally, some conclusions. And before I finish, and if I have time, I would like to give some information about the international Congress that we are organizing in Mexico. So anyway, okay, I will continue now with the presentation. As I said, I will give you a general introduction about carbon materials. Some of you already know that carbon materials is an amorphous structure, form made of graphitic layers. This material is highly porous, has different size of openings that are named as micro, meso, micropores. And also this material, of course, is made of graphitic layers that are decorated with some groups, usually oxygen-containing groups. Within these, we have the acidic groups like carboxylic, lactonic, and phenolic that usually will give you a negative charge depending on the solution pH. Also, we will have basic sites like pyrrole and chromine that usually will give you a positive charge. And we need to remember also that the graphitic layers have an sp2 hybridation. It means that these graphitic layers will have delocalized pi electrons. And so these materials can conduct current, can share electrons. And so these materials are very important nowadays, as I will mention later on. These carbon materials are very interesting because they can be modified. I mean, their chemical properties can be completely changed. We can remove oxygen groups and include other heteroatoms like nitrogen, like sulfur, to make it more selective, for example, for certain molecules or contaminants. Also, this material, I mean, we can change its textural properties. We can close pores, we can open pores, and so on. So this material is very versatile and again has many applications. And this research area of carbon materials has been very relevant in the last decades because, as you can see in this slide, this research area has been granted with 3 Nobel Prizes. First, in 1991, Professor Iijima from Japan got the Nobel Prize for the synthesis of carbon nanotubes. Later on, in 1996, Professor Kroto, Korl, and Smalley got the Nobel Prize for the discovery of fullerenes. And the most recent one that has been given to Professors Andrei Geim and Kostya Novoselov in 2010 for the isolation of graphene. So, as you can see, this is a resume of the great importance of these carbon materials, and of course, this related also to nanotechnology. These kind of materials now are part of many materials or many equipments now these days. You can see that batteries now have graphene oxide. Many electronics have carbon material. So this again area of carbon materials has been very important. Now, if we talk about the application of granular materials, again, carbon-activated carbons, we know that we have main sources like a coconut-based activated carbon, we have wood-based activated carbon, we have the mineral carbons that already Dr. Cesar mentioned. So these materials in a bigger size also have many applications these days. As I show you in this slide, the demand of this carbon material in 2022, the demand was more than 7,200 million tons. That's a huge amount. And this material is being used in many applications like water treatment, air purification, pharmaceutical and medical, food and beverage. In the automotive industry is increasing a lot. For example, in China is used a lot as a heating material, you know. So this, again, activated carbon in a bigger size, in a particular size, still is used a lot now in these days. And as I mentioned also, if we move to the nanotechnology, carbon nanotubes, graphene oxides, of course, has been very important in the development of many equipments and devices. Okay, now I will talk a little bit about the research I'm doing with my students in NIPICIT in Mexico. These are only some examples. We are using carbon materials combined with metal oxides and hydroxides as absorbent materials to remove metals, to remove hydrocarbons, now working in CO2 capture, and also in the removal of volatile organic compounds. We have used also these materials as redox mediators, combined with biological processes. Also, we are studying the technique or the process of electroabsorption, where we combine, of course, materials with electrochemical processes. This in collaboration with my colleague, Dr. Luis Felipe, that we'll talk later on. Also, we have studied the interaction of carbon nanomaterials like graphene oxide with different bacteria, which is very important also. Also, we are producing different carbon materials for solar cells, like carbon quantum dots these days, from waste, for example. And also, we have used carbon materials as anti-corrosive coatings to protect valuable metal like gold and silver. So these are examples, the research, again, I'm conducting with my students in NIPICIT, and today I will give just a few examples. The first topic I would like to take is the hydrocarbons decontamination. Okay, in this case, I will concentrate just a little bit, because we don't have too much time, about the diesel contaminated with sulfur and nitrogen compounds. This has been a big topic in the last decades. As we know, diesel is used still around the world. And in this graph, I just want to show you that even in this year and in the years to come, according to Mobile Exxon, the amount of diesel will still increase in the last years. Gasoline, apparently, the consumption of gasoline will be a little bit down, but diesel still will be used at least to 2040. So still, we have 20 more years of higher demand of this hydrocarbon. What's the problem with diesel? That the diesel during the combustion, of course, will produce particulate matter. Also, will produce different gases like NOx and COx that are very contaminants that pollute the environment. And some of these contaminants will produce acid rain. So we want to use diesel, but as pure as possible. And so also here in this slide, I just wanted to show you that 15 years ago, 20 years ago, the concentration in diesel, talking about sulfur content, was about 500 parts per million. But now in the last years, the new regulation forced these petrochemical industries to reduce drastically the concentration of sulfur, for example, from 500 to 15 parts per million. So for that, of course, new technology and new materials are needed. The diesel, the composition of diesel, is quite complex. We know that it's made of paraffin, also of monoaromatic hydrocarbons, the aromatic hydrocarbons, and of course, it has sulfur and nitrogen compounds, which is the main problem. How to get rid of these contaminants? Well, these contaminants that, for example, these molecules that have sulfur in their structure, like DVT and DMDVT, are very dangerous pollutants. Also, indole and quinoline. Here, the dot, the orange dot, represents the nitrogen compound. So these molecules again are contaminants, and we need to get rid of them. So what have we done? Well, we have designed different carbon materials to remove these contaminants. So as you can see in this schematic, these molecules can remove on the graphene layers by pi-pi interactions. But also we can increase the removal of these compounds when we include in the activated carbons metal oxides like iron. Here, this iron oxide can give you negative and positive charge. And so these charges can interact directly with these sulfur and nitrogen molecules. So that scheme will explain how we can remove these contaminants. Here in these graphs, I don't want you to see all the numbers. I just want to make an example that when we use only granular activated carbon, these are continuous experiments, vector curves. So we can see that well, in the axis we have the bed volume. When we have only granular activated carbon, the initial vector can occur, for example, at 10 bed volumes. But once we modify the carbon material with metal oxides, you can see that the sorption capacity increases a lot. In this case, the initial vector, you see, it was shifted even to close to 40 bed volume. So 4 times more sorption capacity, just by including, again, metal oxides like iron. So that's important. And this technology, we have even applied it at big scale to decontaminate water with hydrocarbons like diesel. So we have installed so far 5 water treatment plants at mainly at the international airports, plants that treat 200,000 liters per day. So all these water treatment plants are based on absorption. Okay, and of course these big columns now you can fill them with these modified materials, and these plants are very efficient. Okay, so again, we have to work at lab scale, but I always push my students to think in the real application. Let's go and apply it, you know. So it's not easy, but it's possible. So this is one example. Even I involve my students in the installation of this kind of plans to get the feeling, okay, how we can solve a real problem. Anyway, so this is an example about removal of hydrocarbons, and as I said, also purification of diesel in this case. Now I will shift to the arsenic problem. Okay. We know, of course, everybody, we know that we have many kinds of contaminants in water, like, of course, we have ions, we have dyes, we have pharmaceuticals, of course, we have microorganisms, we have hydrocarbons, solvents. All these kind of contaminants are increasing day by day in the water. And so, like one of the major contaminants we know is arsenic. Okay, arsenic is in many countries around the world. Of course, we have it in Mexico. Definitely, you have some problems in China. And we know that nobody wants arsenic. Arsenic is a poison. Okay, it produces many types of cancer. Thousands of people still are dying per year, you know, around the world. And we know that the regulations now, they establish that we should have no more than 10 parts per billion in drinking water. So to reduce the huge concentrations that we have in some water source that can even have parts per million, to reduce it to 10 parts per billion is quite a challenge. So we need very good materials with good performance to reach those very low values. Well, what have we done to face this problem? When some years ago we said, okay, let's synthesize some metal oxides and hydroxides, but as small as possible. We know that if we reduce the particle size, we will expose the surface area. If we have a bigger surface area, then we are expecting a higher absorption capacity, for example, for arsenic. We know, and has been published many times, that, for example, iron oxide is very selective for arsenic 5. Okay, we know that the mechanism has to do with hidden sphere complexes, bidentate or monodentate. And again, if we reduce this particle size, the surface area will increase, as I showed in the graph. And so hopefully we will have a very good absorbance. One of the problems is, okay, if I have very small particles, then how can I remove these particles? Okay, these particles cannot go in the water. We cannot drink them, otherwise the problem will be worse. So what we have done is we have anchored this kind of particles on activated carbons. Okay, in this case, for example, we managed to anchor particles, iron oxides and lanthanum particles on activated carbon that go from 15 to 300 nanometers. But if we use a Kepin agent, as I will explain in the next slide, we managed to reduce quite a lot this particle size of this metal oxides to 3 to 10 nanometers. And the dispersion of these particles on the carbon surface is very homogeneous. One of the challenges is not to block the porosity of the activated carbon. So here, as an example, I show three materials with different surface area. Once we, for example, anchor lanthanum, the surface area decreases. But if we use a Kepin agent, we manage to keep the surface area. Even in some cases, it increases a little bit. We have a better dispersion. And in this case, the metal oxides is not just impregnated on the surface. This is actually anchored on the surface. Again, this is very, very important. And this is the mechanism we have published it many times. If we don't use a Kepin agent, the cluster of the metal oxides can increase, okay, and then we will end with a quite big particle. But if we use a Kepin agent as phosphorus, for example, in this case, we manage to block the growing of the metal oxide. And then with a simple rinse with water, we get rid of the Kepin agent, and we end with very small particles. And that's very important for the application. Okay. In that case, the arsenic will remain on the material, and the metal oxide will not leach to the treated water. That's very important. Well, in this case, of course, as you saw in the last slide, the metal oxide will anchor on the oxygen-containing groups of the carbon material. Okay, so we can anchor a different metal oxides. In this case, you can see in red dots. Well, one of our ideas, okay, I want to increase more the concentration of metal oxide, aiming a higher sorption capacity of arsenic. So we said, okay, what if we oxidize the material? We will increase the amount of nucleation center. In other words, we will increase the concentration of the oxygen-containing groups, and then we will have a higher concentration of metal oxides, and with that, a higher sorption capacity. That was the idea. This was a thesis of one of my students. And then, surprise! I want to show you. I don't want you to see all the numbers. What I want to show you here is that the material that has more metal oxides doesn't have the most or the higher sorption capacity. And so what is the answer? And is that if we oxidize the material, then we will include more metal oxides, but not all the oxygen-containing groups are capable to anchor metal oxides. And this, let's say that these oxygen-containing groups that do not interact with the metal oxides will give us negative charge. And so, if we have again a material with a lot of metal oxide, this is the surface charge distribution. As you can see in this example, its surface is very negative, and that's not good for the sorption capacity. So we need to have a balance. In other words, I show you here in a schematic. If we have a material with a lot of metal oxide, but also with a negative charge, we will have repulsion of arsenic 5. But if we have a positive charge and also metal oxides, of course, the absorption capacity will increase. So here the message is we need to have a balance, okay? And this is very important. Well, that's what we learned from arsenic removal. Also, we have, apart from using metal oxides like iron and lanthanum, in the last year, we have anchored mixes of metal oxides like combination of iron and manganese, iron and cerium, zirconium and cerium, and we have obtained a very good material. We just published the results, a material with a very high capacity of more than 180 milligrams per gram, which is quite a lot, and we just applied for the patent, and so we are very happy for that. Another advantage of using mixes of metal oxides is that these will be more stable. In other words, they will not leach as easily. And we will also have very amorphous materials with higher surface area. And this will give us much higher removal of arsenic. Applying these mixes of metals, we have obtained different shapes of metal oxides. As you can see here, like we have obtained this kind of stars. We have obtained also peanut-like shape, this kind of plates and prisms, arcing also. And recently also when we mix iron with magnesium, for example, we obtain interconnected fibrils with also very high capacity for absorption capacity. As you can see, these materials are quite small and very amorphous. So it gives you very high surface area and very interesting absorption capacity. We have published also these results. Now I want to move to the carbon dioxide topic, which is very interesting these days. We know that environmental pollution is important. We know that the concentration of greenhouse gases, is increasing a lot. Of course, this has changed in the climate, and this is leading to the global warming. Okay, we also know that carbon dioxide contribute to 66%. So it's very important to target this contaminant. And of course, we know that around the world, the government has a lot of agreements, to reduce the CO2 contamination as much as possible. What is the reason? Well, we know that this is global warming, but if we see the concentration of this contaminant, if we go back to 1750, the concentration in air was 278 parts per million. Just the report of 2021 was 216. That increased a lot. But if we continue like that, in 2050, the concentration of CO2 will be 550. Of course, this will change everything, and is changing everything already. Everywhere, in Mexico, in China, everywhere, the weather has changed a lot. Just as an example, just in July last year, I attended the Carbon Conference, the World Carbon Conference that was in London. And we were at 32 Celsius degrees. This never happened in London. I mean, it was, for me, was a shock because I lived there for 3 years. I did my PhD there. And the weather in London was very bad. Always raining, always cold. But in this time was even hotter than in Mexico. I mean, I was so surprised. Anyway, everything is changing. So what is causing this high concentration of these greenhouses in environment and especially carbon dioxide? We have fires, you know, we have big droughts and big floods. Also, the ice in the poles, you know, I mean, it's very bad, you know, it's melting. And this is causing that the level in the sea is rising. And I mean, so many problems. And we are here, I mean, close to a little bit more of 460 parts per million. But it's increasing, it's increasing, it's increasing. And so, okay, we need to do something about it. This is, let's say, a hot topic now these days, and so we are trying to contribute a little bit to this matter. So we need to, in this case, to stop the production of carbon dioxide, or go to another way. And okay, what can we do to capture this CO2 and reuse it, instead of producing more CO2? Because as you know, CO2 is used in industry in many ways, okay? In food industry, in the production of fuels, in greenhouses, in beverages. So, and for this, CO2 is produced. So why not we capture it and reuse it? We can take it directly from there. And that's one of the proposals. So we are working on that. We know that the process of absorption with B has been applied already. This process uses liquid amines, and unfortunately, it has some drawbacks, like it's very corrosive, is thermally degraded. He needs a lot of energy for the regeneration, and that's a big problem, because if you need energy, then you will produce more CO2. So another technique that is used is, I mean, it's in a study these days, is absorption. And so many materials have been tested these days, like zeolites, mesoporous silica, metallic organic, or los frameworks, alumina, and of course carbon materials. And later on, I will explain why carbon materials can be very selective for CO2. So in this case, if we use carbon, this kind of materials, we know that can have fast kinetics. That's important. Fast kinetics is very important. Also, of course, high capacity. These materials need to be selective, need to be low cost, especially produced from wastes, okay? And also have to be regenerable. That's a key factor, okay? So in that respect, in my group, we have already published some papers that report the use of biochar impregnated with ionic liquids, very selective for CO2. Okay, but I mean, continuing with my talk, and as I say in the beginning, I would like to mention what we are doing with biochar combined with carbon nanostructures, and we are doing some work in that respect. Sorry, I will go back. Again, here the idea is to capture the CO2, concentrate it, and then reuse it. For example, in greenhouses. That's one of the main ideas. Okay, what are we using as a substrate to grow nanostructure, and especially carbon nanotubes? As you know, Mexico, we like tequila. Hopefully you like tequila also, of course. And Mexico is the main producer. And we produce about 6,100 million tons of bagasse per year. That's a huge amount. Okay? Maybe you don't know, but we need 20 kilos of agave to produce 1 liter of tequila. 20 kilos per 1 liter, okay? That's quite a lot. So we are using these waste to produce biochar, these very nice fibers that have huge pores from tip to tip. So it will help us to have very good kinetics. Okay, so we are using this substrate. Then, of course, we need to impregnate. In this case, we need to deposit, to spread the catalyst on these big pores. So we are using iron 3 and iron 2 to produce this kind of metal oxide, which will be the catalyst to grow carbon nanostructures. And then, of course, we need to, in this case, we are using microwave to reduce the synthesis time, because we can produce this just in a few minutes, and the material is ready, the catalyst is ready, is deposited on these big channels. Of course, we are playing with different concentrations. Once we have the catalyst, we apply a carbon vapor deposition. This is the basic methodology. And in this case, we are using acetylene as a carbon source, okay? And we synthesize these nanostructures just in a few minutes, 2 to 10 minutes, the material is ready. Of course, we need to control the concentration, the temperature. As you see, we are using between 500 and 800 finally to grow these carbon nanostructures and as homogeneously as possible. So once we have that, we have a micrograph of, after a few minutes, we synthesize these carbon nanotubes. These are already anchored, also very important, anchored on this very nice biochar, so this very nice fiber. As you can see here in the tips, the catalyst is ended on the tip, okay? And here, something very important is that the aim is to increase drastically the surface area. So if you can see here, the fiber, natural fiber, the carbonized fiber, has a very low surface, close to 2 square meters per gram. But once we grow carbon nanotubes, the surface increase up to 250 square meters per gram. This is very important because all this area is already exposed to absorb CO2, okay? Some materials, of course, can have very surface area, but these materials are microporous or mesoporous, so we will have some diffusional problems. In this case, no, because these carbon nanotubes are inside these big pores of the fiber, so kinetics are very fast. Okay, here's some results. This is at atmospheric pressure and 25 Celsius degrees. If we compare the black line with the blue line, the blue line is the material that has the carbon nanotubes. We already increased the absorption capacity from about 1.1 to 1.5 millimoles per gram, which is very good, and this is related to surface area. Kinetics is very fast, as you can see, very fast, because some materials can take hours and hours to reach equilibrium. In this case, in few minutes, you saturate the material. That's very important. Well, now, if we apply pressure, you can see that for the material that has the carbon nanotubes, increase the capture capacity of CO2 quite a lot. Even at 10 atmospheres, which is not a very high pressure, we already have a capacity close to 3.5, 3.7 millimole per gram. Now, it has been established that the minimum capacity required for an adsorbent material is 2 milligrams per mole. So we already are above that capacity. So we are very happy about that. We just submitted this data. These are quite new and I think are quite important. Another question is, okay, is the material regenerable? Because otherwise it's not a good material. Well, in this case, we have at atmospheric pressure and 25 degrees, we have the cycles of absorption, desorption. And as you can see, okay, again, the kinetics are very fast. So when it goes up, it's absorption and then desorption. Absorption, desorption. And so the regeneration capacity of the fibers is 99%. And the material with carbon nanotubes is 95%. But this is at 25 degrees. If we increase a little bit temperature, the regeneration is 100%. So this is also very good because we can reuse the material n times. That's very important. Okay, now one of the questions is how CO2 can be adsorbed on carbon materials. Well, in this case, the mechanism is quite complex, but of course, as in this scheme I show you, of course, the CO2 will interact with the oxygen-containing groups because we need to remember that CO2 has a quadrucolon moment, and so we can interact by electrostatic interactions. Also remember that the graphitic layers in these kind of materials have delocalized electrons, and so this sp2 hybridation, of course, this can interact also with this molecule. Also, we will have the edge sites on the graphene layer that is rich in electrons and in negative charge, and these will interact also with the CO2 molecule. Okay, and of course, we also can have this kind of interaction between neighboring CO2 molecules, like in this case in the index. So this is very important. This is when we have a graphitic layer. But then remember that we are growing carbon nanotubes, that of course CO2 will interact directly in the carbon nanotube also. We have more area, but we have also more active sites. We have the graphitic layer, in this case in form of tube, but it still will give a lot of active sites to remove CO2. Okay, so the mechanism is not simple, but there are different ways that in way that this molecule can interact with the surface of these materials. Well, almost to finish, because then I will take a few minutes to give you some details about the international conference I was telling you. Final remarks, of course. Nanomaterial science allows to synthesize more efficient macromaterials. Okay, mineral oxides and hydroxides are essential in diverse areas, like in catalysts, absorption, precipitation, coagulation, in many areas. So that's why this new journal that Professor Song is leading is very important. I'm pretty sure they will receive a lot of papers. Then the correlation between chemical and textural process and textural properties, talking about carbon materials, is essential to understand and to improve processes, okay, from lab scale to big scale. Also, we need to keep in mind that our experimental methodologies should be established, keeping in mind their scalability, because sometimes we can produce very nice material at lab scale, but sometimes the chemicals are so expensive, or you cannot find them easily, and then when you want to scale the process, it's not possible. The cost effect is very important. And finally, multidiscipline emphasizes even more the great importance of carbon-based materials. In other words, I mean, I'm collaborating with a specialist in electrochemistry. I collaborate with a specialist in bioprocesses and so on, because I don't know everything. I know a little bit about carbon materials and characterization, but if I really want to apply this material and to really solve problems, I need to collaborate with a specialist. And that's very important these days. We cannot do everything. Okay, that's important. So that's final remarks about the general topics I just mentioned. Now I will take just a few minutes to announce this. Some of you already know that we are organizing the World Conference on Carbon, and that's the most important in the world. This conference started 70 years ago, 70, and it will happen for first time in Mexico. So we are very happy to organize it, and we are inviting everybody to join us. It's a very nice conference, as you will see. I have the big responsibility to be the chairman of this conference, and I'm sharing the responsibility with my colleagues and friends, Professor Mauricio Terrones from Penn State, from USA, and with Carlos Moreno from Uniandes from Colombia. We will have these 9 topics during the conference. So as you can see, it's very general. All the topics regarding carbon can fit in. So we have carbon in biology, medicine, and health. That's a very important topic. Carbon in environmental applications. Of course, Dr. Song and all his team is working very hard on this. Carbon in electrochemical process and technologies. We want to bring the electrochemists because they use, of course, electrodes made of carbon, and we need to make the match. Innovative carbons, like the new generation of materials like MXenes, heteroatoms, nitrides, very important. Graphene and graphite, catalysts, carbon fibers and composites, coal, coke, and carbon black. Also, China, very, very important in this topic. And also a very nice topic is with diamond. Okay, so the web page, of course, is active. You can check all the details there. Also, talking about the deadlines, the first deadline was already passed, was the 30th of December. But the good news is that we just extended to January 27. So you still have time to submit your short abstract. Short abstract is no more than 250 words, very concrete. So we are looking forward to receiving your contributions. And as I said, this is very important. It's the most important conference in the world of carbons, and we will have the pleasure to have Professor Sir André Geim, who is the Nobel Prize of Physics of 2010. He is from the University of Manchester, United Kingdom. So he will give the opening plenary conference, and I'm sure it will be very, very interesting. So I hope you will join us there. We also will have Professor Hirotomo Nishihara from Tonoku University from Japan as a plenary conference. We also have Professor Magdalena Titirici from Imperial College London from United Kingdom. We will have Professor Alberto Bianco from the National Center for Scientific Research from France. And the scientific committee, this is just an example. There are many others. We have the top researchers in the world in carbon materials, very, very important scientists. Of course, we have people from China, and I want to highlight that also in the international organizing committee, we have Dr. Fei from Wuhan University of China, and also Dr. Xia Wei from University of Mining and Technology of China. So they will join us in this Congress, and you need any information, and you can talk to them because we have a direct link, and we can solve any problem. If you need a support letter for visa, we already have it, no problems. So you can apply for visa in advance, And again, we will be very happy to receive your contribution. This Congress will be happening in Cancun, which is a very famous place around the world, and will be happening in this very nice venue, Barceló Ribera Maya, which is a big complex, very beautiful. Next, I will show you a very short video to see if I can convince you to join us in Cancun. So I hope you can listen properly. Okay, well, I hope I have convinced you, and please join us. We will have a nice top science, and also we will have a lot of fun. So please send your abstracts, okay? And see you in Cancun next year. Thank you very much. And for me, I just want to end with the acknowledgements, of course, to the companies and institutions that have provided me money to conduct my research, and very important thanks to all my students that, of course, they do all the hard work, and so thank you very much to all of you. Professor Song, thank you again. Always a pleasure to be with you. And there is my I leave my email address. if somebody have a question and a comment, I'll be very happy to answer. So thank you very much.
Okay, thank you very much, Rene. Okay, very good that presentation. Okay, you did that. You shared that very good results that with us. Thank you very much. Yeah, you know that just like I think that we don't have that enough time to have that deeper discussion. So I would like to say that please just give that your presentation about that the carbon conference to Vivek. I think that we can distribute that the videos to our colleagues. So you know that China has opened that the door to go that abroad. So that's a very good news for us. So our colleagues can go to the Cancun that's here. So that's no problem at all. That's very good. So you know that 1 month ago that I scared that we have that we can go, but that's China that's very structured. So I think that we can organize that very good Chinese teams to go to that Cancun. So even that I don't think that all of that people will send the architect. I think maybe it's about if we send that 20 architects, we will have that 40 attendants, something like that. Okay. So yeah, that's I just say that something like that. But anyway, that we will get more the architect to go there. So I think that you will have the large Chinese group to join that carbon conference. Okay.
Yeah.
So and Sharon. So I would like to please to your community to to distribute the conference carbon 2023 in Cancun. Okay, thank you, Sharon. Okay, okay. So finally, I would like to say that thank you very much, my good friends Rene, to share with us your work in ether, in carbon, CO2 captures, and also with the removal the advantages. So you know that in my group, I have the same interest with the topic. So I think will the China opened the door. So I think we will have more opportunity to work together to will apply our technologies in Mexico and also in China. Okay, thank you very much. So finally, just to give very warm approaches to Dr. Rene. Okay, thank you very much.
Thank you. Thank you.
Thank you. Okay, so our next speakers will be Dr. Luis Chazaro Luis. Dr. Luis obtained his PhD from National Polytechnical Institute, Mexico. Now he's associate professor in EPC. He worked as postdoc in Leibniz Institute of I don't understand Germany, but that's the one institute in Germany. Now he's the member of national system of the researchers level 2. So he has published 47 JCR papers and 1 chapter of the book and one that partners. So now let's welcome that Dr. Luis to give us that the seminar. Please.
Thank
Luis.
you. Can you hear me?
Yes.
Thank you. Thank you very much. Good morning over there. Hi, everyone. First of all, I would like to thank to Professor Song for the invitation and his team from Minerals and Mineral Materials Journal to have the chance to present my work in this seminar. So I am Kemes, and as you are, well, I'm going to start to share the screen.
Okay. Yeah, we can see.
Okay. Okay. So then, this is the title of this presentation, Advantages of the Electrochemical Properties of Carbon-Based Materials for their application in environmental processes. The good thing is that the previous speaker, Professor René Rangel, gave a very nice overview of the properties and the advantages of the carbon materials. So then with this information will be very useful for the examples I would like to share with you. I am Kemes, and as you already know, I also work in the same institute and the same department of environmental sciences. So I have the pleasure to collaborate with my colleagues and friends, René Rangel and César Nieto. Here, this is the picture of the institute, and René already showed the location of the state of San Luis Potosí, but I would like to remind you this location because it's important for the examples I'm going to talk about. So then, briefly, I'm going to mention what we do in environmental sciences, and then I'm going to talk about a water treatment process, which is called electroabsorption. And I'm going to focus on arsenic and fluoride. And I don't think I will have time to talk about environmental barriers, so I will just mention these two examples. So then, as you can see here in my case, I work in environmental electrochemistry. And electrochemistry is by definition an interdisciplinary science, which means that you can easily collaborate with other disciplines. For example, science materials, and of course, science of carbon materials. And also I collaborate with some ecologists or some biotechnologists in the same division where I work. Part of the things that we do are bioelectrochemical systems, and for those we use carbon materials as electrodes, especially to develop some electroactive biofilms in systems like microbial electrolytic cells or microbial fuel cells. René already mentioned that we work in the development of carbon materials, especially for synthesized solar cells. Also, we have worked in electrochemical sensors with carbon materials. Like in this slide, you can see that we develop elements of molecular recognitions that we immobilized on carbon materials like graphite or glassy carbon or carbon-based electrodes. And these other two examples are also mentioned by René, but additionally, we work with bioelectric systems in collaboration with the biotechnologies, in which we stimulate or we stimulate the living microorganisms with an electric field. So then we change the metabolism, to produce some things that are useful, like hydrogen, or for example, for remediation, or some solids or water. So this is important. In the case of electroabsorption, we also apply this to the removal of organic compounds, like those from the pharmaceutical industry or from the textile industry. And all these systems or all these topics have in common that we use carbon materials. And as René mentioned, the advantage or one of the main advantages of these materials are their electrical conductivity. But other advantage is that the morphology and the chemical surface, the chemical properties on the surface can be modified in order to modulate the material for the application that we are interested, like, for example, supercapacitors, batteries, electrochemical sensors, or photodetectors, or also in the last years, for example, conductive textiles. So then, so it depends on what we would like to do. Then we need to choose the morphology, So then this is the important thing. But in this presentation, I'm going to focus on the importance of the correlation between the electrochemical properties and the textural and the chemical properties of the carbon material. And then I'm going to start with the first example. I'm going to start with the electroabsorption of arsenate. And in this case, one of the important things is that in the state of San Luis Potosí, two of the main economical activities are the mining industry and the manufacturing industry. So then these are the main sources of pollution in air, soil, and water. So, but this state is located in part of the semi-arid region of the country. It means that one of the main sources of water is the groundwater. And the groundwater contains arsenic, but usually together with fluoride, in addition to these other elements. So this couple is common to find it in together, in different concentration, but they usually are together. And this is because the minerals which contain arsenic are in contact with the groundwater. And usually the concentrations are above the maximum allowable limit, which is 10 parts per billion. So this is a very serious health problem in this state, and also in the neighbor states, especially in the north of the country, which all these states are located in the desert Chihuahuense, which means that the people usually consumes groundwater. And the problem is that this water, although is good for human consumption, it contains higher concentrations of arsenic and fluoride. There are several technologies to remove arsenic, as you can see in this treatment train in this slide. For example, coagulation flocculation, also absorption. But if we, let's see. If we combine one of these technologies, for example, we can design a hybrid technology for arsenic removal, like absorption and an electrochemical process to develop electroabsorption. And as mentioned by Professor Rangel in the previous talk, arsenic is an environmental problem, no? So then we have been working in the study of electroabsorption, but the question is, in which part of the train, of the treatment train, would absorption be applicable, no? So when absorption decreases the concentration of arsenic, no, like here, but the concentration is still slightly above the maximum allowable limit, the absorption can no longer contribute to the removal. So then is the moment to apply the electroabsorption. And the electroabsorption can remove organic and inorganic ions from the water. The electroabsorption consists in polarizing conductive absorbents, such as activated carbon, and these materials provide high surface area to promote the migration of the ions to the electrode surface with the opposite surface charge. And the process is like the capacitive deionization process for desalinization of water. No, this is an example. Here, for example, this is an asymmetric cell where you can see the anode, and this is the cathode. This electrode is made with activated carbon, is a granular activated carbon, is PAC. And we can take advantage of the surface, of the porous surface, as it was explained by René in the previous talk. So then when you apply the potential, you can see that the ions are accumulated in the porous structure. This example I'm going to talk about is studied by my PhD student, Rigoberto Santoyo. And in this study, we use activated carbon of mineral origin, which is F400, which is a commercial carbon that is widely used in water treatment. And it was used in its granular form. So this was packed and used as the working electrode in an asymmetric cell with 3 electrode arrangement. It means that we have a reference electrode, no, to monitor what the working electron is doing. The pristine electrode, which is the blue color, the profile, shows an alkaline character, as you can see. And this material was subjected to a thermal treatment. to increase its alkaline character, and its degree of reduction and its positive surface charge, which contributes to favorable electrostatic attraction of the arsenate or arsenic anion. No? And as a control, this material was subjected to an acid treatment that increased its degree of oxidation, of course, its acid character, and this in turn causes a greater density of negative surface charge, which contributes to an electrostatic repulsion of the arsenate. And these profiles are consistent with the type of oxygenated surface groups, since the material with an oxygenated or with a higher acid character presented a higher number of carboxylic groups that are ionized at pH above 4.5. And these treatments did not significantly alter the texture of the materials, as you can see here, because they maintain a similar surface area. And instead, there was an important change in the surface chemistry, which is the effect that we wanted to study in the electroabsorption of arsenate. Here you can see how the chemical properties of the material change with these treatments. And here are reported the point of zero charge, the total of acid groups, but this material also contains a small percentage of iron oxides, which contribute to the chemisorption of arsenate. So then the texture will not influence considerable the performance of the material, but instead the chemical surface. Here in this slide, we also noted that these materials exhibited a nearly rectangular voltammetric response, which is the typical response of an electrochemical capacitor, where the response of the most oxidized material, which is the blue line, also presented a contribution of secondary Faradaic reactions that may not favor the electrosorption process. That what we want is a more capacitive materials, like the red and the black line here. And what is the origin of these secondary reactions? Where, because this material has a considerable amount of oxygenated groups, which are susceptible to the reversible oxidation or reduction reactions, which are shown here. But these reactions are considered like parasitic, They affect the performance of the electroabsorption. So then this is consistent with this polarization profile, the red one. In this case, you can see that the more acidic material oxidizes at lower overpotentials than the other materials, which gives it gives a disadvantage for electroabsorption. So, and other reactions that we have to consider are the electrolysis of water during electroabsorption, or the oxidation of the current collector, which is used for the packing of the electrode. So then we have to make the list of all the possible oxidation and reduction reactions that are possible in order to avoid them during the process. Here in this slide, when the pristine material and the material with the heat treatment were used as anodes, this is the pristine and this is the material with a more reduction degree. And the material with the highest degree of reduction increase the rate and the capacity of the arsenate absorption compared to the pristine material. And what we have to pay attention is that at 0.4 volts, the electroabsorption capacity of the material at equilibrium was lower than when the material was not subjected to an electrical stimulus, which is called OCV in this case. This indicates that an overlap of the double layers has occurred at this potential, and then the pores of the materials are obstructed, no, or obstructs the entrance of the arsenate. No? So, and in the other cases, like 0.8 and 1.2, you can see this increase in the absorption capacity. So then the thermal treatment of the material provided a contribution of the 70% of the absorption process, while the potential or polarization of the electrode contributed with the 18.5% to the increase in the absorption capacity here. No? So then is so this is an important performance of the electrode. And in conclusion, we can see that the higher degree of oxidation of the material, the higher the electrical resistance and the less available polarizable area, which is also has an impact on a lower absorption capacity of the arsenate, no? In contrast with this electrode. So now I'm going to present the second example, focus on electroabsorption of fluoride. And this study considers the textural, the physicochemical, and electrochemical characterization of the electrode material and its performance with electroabsorption of fluoride. So then, in the case of fluoride, this is an essential element for human health, but at low doses, no? So it means that its excessive and chronic consumption promotes undesired health conditions like dental weakness and skeletal deformation. So the World Health Organization established a maximum concentration limit of 1.5 parts per million. So it's a little bit higher than in arsenic, in the case of arsenic. And in the case of Mexico, the concentration of fluoride in groundwater exceeds this maximum limit. And as in the case of arsenic, fluoride is found naturally in groundwater because it's in contact with the water is in contact with highly soluble fluoride-bearing minerals, such as fluoride. And as I mentioned before, the groundwater is one of the main sources of water in the northern states of Mexico. Of course, as in the case of arsenic, there are several methods to remove the fluoride, like ion exchange or electrocoagulation, electrodialysis. But usually these two, especially these two, are a little bit more expensive. especially when you use, for example, membranes. No? And that's why we propose as an alternative electroabsorption. And there are recent reports related with fluoride electroabsorption using carbon electrodes, but modified with titanium dioxide or titanium hydroxide, in which their electric polarization promoted an increase in the removal capacity and velocity compared to the pristine carbon electrode. And these are the starting concentrations that they use in their studies. And in the case, for example, of Lee, I remember that they have focused on fluoride electroabsorption using micropore dominant activated carbon electrode. And they attain a very high charge efficiency. No? So then the question is, of course, what is the effect of the texture, or what is the effect of the modification, for example? No? In our group, and in collaboration with René Rangel, we have studied the absorption process of using granular activated carbon impregnated with hydroxyl lanthanum 3. And as you can see here, it was observed an abrupt increase in the absorption capacity and velocity of the commercial activated carbon F400 after its impregnation with lanthanum 3, because the presence of these hydroxyls is fundamental, since they can act as exchangeable ligands with the fluoride in the absorption process. So it's a chemisorption. So even though the impregnation of lanthanum was optimized, the absorption process performance was very good, but decreased when it was evaluated in tap water due to the competition with other anions. No? So then there are also several reports on the capacity properties of specific lanthanum compounds, which may favor the electroabsorption capacity of a hybrid lanthanum carbon electrode. So the hypothesis was that if what was much more important, the capacity properties of the lanthanum or the intrinsic properties of the carbon material. So then we decided to study or to propose 3 objectives. The first one was to study the influence of a minimum amount of lanthanum to promote a better dispersion of this element or lanthanum clusters, and thus to avoid the occlusion of the micropores of this material. Also to study the influence of the amount of lanthanum and the changes of the textural properties, as you can see in these 2 figures. And also we studied the competition with other anions of environmental importance, but I'm not going to talk about this. I think I don't have enough time for this. So only these two aspects. So in this slide, you can see that a low amount of lanthanum doesn't significantly alter the textural properties of the material. So for example, the content of 0.45% decrease only a little bit the surface area of the material. And you can appreciate that the distribution of the pores or the clusters is essentially very well, no? As you can see here. And the pores didn't change significantly after the impregnation. So these clusters were very well dispersed. And also another important thing is that this carbon is highly disordered with irregular pore structure. No? So then in the voltammetric responses of the carbons, a very low scan rate, and this cyclic voltammetry was obtained and sulfate, potassium sulfate, which is inert and also at this electrolyte was at pH 7, was neutral. So, and the voltammetric response resembled a rectangle, no, the typical response of the double layer capacitor. You can observe that there are minimal differences in the current response among both carbons, which implies that the presence of lanthanum doesn't significantly modify its potentiodynamic polarization. And in contrast, the capacitance of the modified carbons decrease with the increase of lanthanum content here. And the textural analysis of the carbons show a marked decrease in the surface area and the pore volumes, as you can see in this figure. No? So the lanthanum hydroxides can anchor, also can agglomerate onto the carbon surface, mainly due to their coordination with oxygenated groups such as phenolic and carboxylic groups. And then for more occluded pores, of course, decrease the polarizable surface of the carbons, which decrease their ability to retain the ions at the interface. No? So this corroborates that the lanthanum clusters block an important part of the polarizable area of the modified carbons, and that polarizable area was located mainly at the micropores. Okay. So then in this slide, you can see that the pristine carbon, which is the black profile, presented an alkaline point of zero charge, no? Was 8.9. And also it presented a positive surface, which is favorable for electrostatic interactions with fluoride, the working pH solution of 7 around here. And on the other hand, the modified carbon acidified abruptly. So then attain a point of zero charge of almost 5, which was associated to the presence of terminal hydroxyls from the lanthanum clusters, means that these hydroxyls can deprotonate at the pH of the working solution. And these deprotonated hydroxyl functionalities confer a negative charge to the surface of the modified carbon. And thus, of course, an electrostatic repulsion towards fluoride. No? However, the presence of these hydroxides, as I mentioned before, is fundamental because they act as exchangeable ligands with fluoride, favoring the coordination of this anion with lanthanum. No? So even though this charge, the chemisorption is still favorable. So then the adsorption isotherms show that the maximum absorption capacity of the modified carbon was almost 8 times higher than that of the pristine carbon. So according to the Black-Muir absorption model. And you can observe that the modified carbon presented a faster removal in a more accentuated slope here, no, compared to the pristine carbon. So the difference is quite clear. So another interesting thing here is a very important electrochemical parameter for electroabsorption is called potential of zero charge. This parameter should be correlated with the point of zero charge. And here, for example, you can see that the point of zero charge is modified or is changed, no? Is more acidic as a function of the increasing amount of lanthanum, and for which their surface will present a negative charge at neutral solutions. And the other thing is that the pristine carbon presented for example, the lowest potential of zero charge, and then this value of the modified carbons is increased to more anodic or positive values as a function of the increasing amount of lanthanum 3, no? Lanthanum 3, as you can see here. So then the increase of this value for the modified carbons implies that they will require much higher polarization values or much higher energy, no, to polarize them, which is a disadvantage, no, for the process. And these higher polarization values are necessary to change the surface excess and also to remove fluoride, no? Here you can see, here I'm showing how the hydroxyls are deprotonated, no? Depending on the pH of the working solution. So if the pH is higher than the 0 point charge, so we have a negative surface charge. So because of the results of the potential of zero charge, the selected half self potentials were 0.4 and 0.8, which are above the highest potential of zero charge for the material impregnated with lanthanum at 0.45%. And also at values higher than 0.8, you can see that the oxidation of the material, especially with the pristine, is much higher. The interesting thing is that the lanthanum protect the material from the oxidation, because here the oxidation starts much higher potentials here, no? The other interesting thing is that we monitor the concentration of lanthanum in solution. We notice that the lanthanum is not, how do you say, it doesn't decoordinate from the surface. So this is another advantage, no? Because you have to take care that the material doesn't release, no, this element of the solution. So then if it's released, you cause another problem of pollution, no? So then we also work with asymmetric cell configuration. It means that only one electrode, the working electron, is packed with the granular activated carbon. As you can see here, it's also an arrangement of 3 electrodes, and we use this system as a reference electrode. In this study, you can see or you can appreciate that the electrosorption kinetics by potentiostatic control of the anode under the application of a step potential. A step potential means that you wait a little bit at the beginning without electrical stimulus. You wait until the system is in equilibrium, and then you start the polarization. No? And in contrast, in this case, the polarization is from the beginning. So it means that you don't expect the equilibrium. So you start the polarization very, very quickly. As in the moment you put the electrode in solution, you start the polarization. So then the first step, in this case, the first step was at open circuit potential. It means without the electric polarization. And during the application of potential, and when the absorption equilibrium was reached, a maximum time of 3 hours was maintained before the increasing of the next applied potential value. And here is shown that both carbons increase their removal capacity at each applied potential. And the absorption capacity of the pristine carbon increased from 1.1 to 4.2 in the last polarization step. And the modified carbon reached almost 6 of absorption capacity. No? And when compared between samples, the effect of the anodic polarization on the removal capacities obtain a mark, obtain a mark and significant increase in the fluoride removal. And when the adsorbent electrode was polarized from the beginning, I mean, as I mentioned, there was no previous step of the conventional absorption. The capacity of absorption for the modified material was lower than in this case. So in this slide, it is shown that the effect of polarization profile on the electroabsorption of fluoride, in which it can be observed that the two modified carbons, this with higher percentage of lanthanum, when they are polarized at 0.8 volts, after the absorption equilibrium, presented higher rate of removal and also higher capacity of absorption. So, and the electrode with a higher amount of lanthanum, so the red profile, obtain almost 9 milligrams per gram, no? Which means that an increasing of the fluoride removal in almost 50%, no? Compared to the absorption and the electroabsorption process individually. I mean, by polarizing, the obtained absorption capacity was 6 milligrams per gram. And this step potential profile increases the absorption capacity because some of these hydroxyl ligands are exchanged by fluorides in solution. And then some of the negative charges on the carbon surface should decrease after the absorption equilibrium. So then this was corroborated by measuring the point of zero charge. No? So then after the fluoride absorption, you can see here the changes. No? So here you have a negative surface or a positive surface. So this parameter shows us the mechanism that I am describing. No? So then, as it was corroborated by these measurements, the point of zero charge increase and the potential of zero charge decrease. No? So then what about the steps of the mechanism? No? Here we can visualize them. So at pH 7 of the working solution, the protonation of some of the surface hydroxyls is promoted, and then some of these hydroxyl are exchanged with the fluoride without the application of the electrical stimulus. So then this mechanism agrees well with the Donans amphoteric model. This model was very useful to describe these results because it says that in a positive surface, or a positive surface is better suited for anion electroabsorption due to a decrease in the energy needed to modify the surface excess. I mean, so you have less co-ion expulsion, or a higher electrode charging. I mean, higher values of potential of zero charge, higher values of over potential. No, these values are higher than the potential of zero charge. Means that that you have more attraction for the anion towards the surface, as you can see here. So then this positive charge can be located on the surface of the carbon material. No? So then there is a synergy between the inner potential, I mean the applied potential of 0.8 volts, and the surface potential associated with electrode surface chemistry. So the global attraction towards fluoride increases with both potentials, increases when both potentials are more positive, and also the step of absorption equilibrium is very important, no? As a previous step. And additionally, it is known that the lanthanum can expand its coordination sphere. I mean, the lanthanum can accept more than 2 fluorides, no? And this is very well described in the literature. So then, as a conclusion, if we increase the amount of lanthanum, then we can provoke that the narrow pores were not only obstructed physically, but also electrically, due to the exposed antagonistic charges from the protonation. No? So we have to take care how much amount of lanthanum we use and how can affect the textural properties. So then the first hypothesis that we propose that the lanthanum can provide capacity properties was not how do you say, so it was not true that these hydroxyls cannot contribute, no, with capacity properties. So it's better, probably it's better to have an oxide lanthanum, for example, no? But we don't know. It's another idea. Also, we also explore the reversibility of the process. This is important, of course, for the regeneration of the material. No? You can see that if we inverse the polarization, we provoke the distortion of the fluoride, reaching almost 50% of the fluorine desorption in the case of the modified electrodes. No? So in conclusion, the electroabsorption of fluorine was favorable with a very small amount of lanthanum. So then I would like to thank the Mexican Council of Science and Technology for the financial support through this project, and also EPCIT, and also our national laboratories located in the Institute, which are the National Biotechnology, Agricultural and Medical Laboratory, and the National Nanoscience and Nanotechnology Laboratory. Also, I would like to thank our technicians for their support, and the students and the collaboration. Here are this is the recent picture of the group. You can see here René Rangel. No? And so I would like to thank these collaborators, but mainly to my friend and collaborator, Professor René Rangel, because he is, as you can see, the expert in carbon materials. So then it's an important work that we have been doing with this collaboration. And you for your kind attention. Thank you very much.
Thank you. Thank you, Luis. Very interesting, yeah. So you made that check. Our group also that work with that same topic, remove of the arsenic and fluoride. So I think that the way that collaboration that in the futures. So of course we didn't use that carbon materials. We use that minerals materials. So
Yes,
I think that
I have seen Professor Song. Yes, of course.
okay. You know that I think that from that 2023 we can get together and that we can work join that project together. I think that we will have that very good features. Thank you, thank you. So you know that in fact I think that here our student professor did have that many questions to use read, but you know that's almost I think that's 3 hours. So in China now it's that lunch time. So we still have that one topic that so please that if you have that any questions that to that Dr. Luis, you can write down that the email to that Dr. Luis. I think that could be that Luis could be that the better to have that discussion that with the email. Okay.
Okay. Thank you very much.
I will say that thank you, Luis. Okay. So that's one proposal again to Dr. Luis. Okay.
Thank you. Thank you very much.
Okay. Next will be that Charlotte. You will present that a little bit about that our journal, yeah.
Yes, Professor. Thank you.
Okay.
Let me share my
Okay, go
screen.
ahead.
Okay. Okay, so I'm gonna make a really brief introduction of minerals and mineral materials. Our journal is an international peer-reviewed and open access online academic journal, and Professor Song is our editor-in-chief, and Jean is our managing editor. So on behalf of the editorial office and the publishing team, I'd like to thank you all for your coming here today. And our journal has a broad scope of mineral researches, including both scientific and technological studies The studies in terms of fundamental materials, new technologies, and new mineral materials will be given preference. And the research topics cover, but not limited to, oil comminution, mineral flotation and interface chemistry, mineral powder preparation and modification, advanced mineral materials, and all the other related topics. And our journal was launched on October 15th, 2021, and we will charge no APC fees before 2025. So if any of you has any plans to publish articles recently, hope our journal could be one of your choices. And this too covers from our two issues published recently. Welcome to read all the articles on our website. And this is our editorial board. We have 34 editorial board members, including one honorary editor-in-chief and one editor-in-chief, and the 2 associate editors. And this is the country distribution of our editorial board. So you can see from this picture, most of our editorial board members come from China, South Africa, South Korea, Mexico, and the other countries or regions. And we still have some seats for editorial board members in 2023. So if you'd like to recommend anyone to us, just be free to contact us. And this is the country distribution of our readership. Our journal has a relatively wide international readership. According to incomplete statistics, the reader group, including the United States, China, Canada, Germany, the United Kingdom, and the other countries and regions. And here's the innovation of mineral and mineral materials. This is our homepage. So you can see some keywords to quick search on the left side and some important links on the right side, like the links to our social media platforms or the links to submit your manuscript of a register. And all the information you may need could be found at this page. And this is the article page. We present some really important data about the manuscripts, like the views, downloads, and even the site numbers for the manuscripts. And if you have many, some special abstracts, like the video abstracts or the graphic abstracts, we could also present them at this page. And this year, we start some new columns like the interviews, webinars, and academic reports. These 2 pictures come from our academic reports and interviews. If any of you has any interest to join these academic activities, we warmly welcome your participation. Okay, so that's the really brief introduction of our journal. And thank you all for your support, and thank you all for your attention. And of course, I'd like to thank you for Dr. Renee, Dr. Caesar, and Dr. Lewis for all your excellent presentations. Actually, we have attracted about 5,000 online audience. Thank you. Professor Song, that's the introduction.
Okay, thank you, Cheryl. Thank you for your presentation, that your introduction about that our journals. Okay, so again, that I want to thank our friend Renee, Louis, and Cesar. That you 3 that you know that in Mexico now, I think that is that 10 p.m. Yeah, it's already that night. So, but even like that, you did that very good presentation and to share with your achievements, recent achievements with us. I think that with that your presentation our colleagues that in China, also in the world, will know that more about your work in Mexico. So I think that we will find that more opportunities to work together in the future. Finally, I want to thank all of you in online and also in meeting rooms. So thank you for your attending our that webinar, and you know that 3 hours that webinar is not normal, yeah. But thank you all of you that stay with us. I think that with the help of that the journal of the Sharon and Jay, we will have more that webinar that in this year. So thank you again. Thank you all everybody. So I will say that goodbye to everyone. So thank you, Renee, Luis, Cesar. Okay. So I think that have that.
Thank you.
Well, meeting that you're all three that in the summer, okay? In San Luis Potosí and also in Cancun, okay?
Thank you very much. Have a nice holidays.
Thank you.
And new Chinese year very soon. Congratulations.
Yeah.
Have a nice day.
Have that 3 weeks for that Chinese New Year, okay?
Enjoy it.
Okay. Okay. Thank you.
Bye.
Okay. Bye. Okay.
Bye.
Bye.
Sharon, thank you.
Okay. Thank you. Okay, fish one.